Before showing a real example, let me first briefly introduce the overall framework of ChromSkills. ChromSkills is designed to help coding agents perform chromatin data analysis in a more interpretable, reproducible, and task-aware manner. Supported analyses including chip-seq, attack-seq, WGBS, and high-C data. The workflow starts from the user. The user provides an analytical request in natural language. After receiving the request, the coding agent first selects and sequences the most relevant ChromSkills for the task. These skills act as modular units of domain knowledge. They encode expert-informed analytical logic, including which steps are needed, which tools are appropriate, and how parameters should be chosen. Once the relevant skills are selected, the agent executes the workflow through MCP-based tools. Finally, the outputs generated by these tools are organized by the agent into analytical results and biological conclusions, which are then returned to the user. Note that ChromSkills can be deployed in any coding agents that support agent skills, and the performance depends on the coding agent and backend large language model provider. Here are some available coding agents and model providers nowadays. In the following quick example, we choose Claude Code as the coding agent and DeepSeek as the backend large language model provider. Now, let me first show you how to use ChromSkills in the Docker environment we provide. First, pull and run the Docker with these commands. Then, enter the Docker container and deploy ChromSkills together with the MCP tools. Next, configure the backend large language model according to the coding agent you are using. Finally, go to the working directory and launch the chat interface. Now, we have opened a chat window for a coding agent equipped with ChromSkills. Here, we provide a prompt for an example chip-seq task involving peak calling and signal track generation. The agent takes a few seconds to think and first inspects the current directory to identify the available input files. It then retrieves the appropriate skills for each analytical step based on the skill descriptions. For example, it uses the peak calling skill for peak calling and the track generation skill for signal track generation. In addition, because the peak calling skill specifies that BAM filtration is required beforehand, and the agent finds the filtered BAM files in the working directory, so it chooses the filtered BAM file instead of the raw one. The agent then detects that each sample has two replicates. Since a replicate incorporation skill is available, it thinks that a replicates pooling step may be required. So it invokes the replicate incorporation skill to pool the replicates first. Then it steps into the peak calling step. Since the chromosome size is required in the peak calling step according to the peak calling skill, the agent tries to infer the chromosome size from the chrom sizes file in the working directory. Then it finds it's a mouse genome, so the corresponding parameter can be set as It's now loading the peak calling skill into memory. Then the agent starts to determine the parameters to use in the peak calling step according to the guidance in the ChromSkills. For example, whether this is a pair end or single end sequencing file, which can be inferred from the BAM files. It also uses the control file automatically according to the guidance in the skill since this is a chip-seq dataset. Note that the agent will query the user for control files if there are no control files provided in the working directory. It invokes the run max2 MCP tools here. Other parameters, like calling broad peak or narrow peak, can be inferred from the type of mark, according to the guidance in the ChromSkills. After peak calling, it steps into the track generation step with the track generation skill. Because the scaling factor is important at this stage, the agent calculates it according to the skill guidance and retrieves the number of mapped reads from the BAM files. It sets the shift TN5 as false according to the guidance in the ChromSkills since it's a chip-seek data. First for H3K4 Me3, then it will process other files sequentially. After completing all steps, the agent generates a report that records the parameters used at each stage and summarizes the results produced throughout the analysis. Now let's see the output in the working directory. Good. As we can see from the output files, the analysis has completed successfully. Finally, let's check the generated tracks and peaks. We can see that H3K4 Me3 shows sharp and narrow peaks with a relatively punctate pattern, while H3K27 Me3 shows a broad and domain-like signal spread across larger regions. So the result is reasonable, and the only thing we need to do during this process is providing a prompt. With ChromSkills, complex chromatin data analysis becomes more transparent, more reproducible, and much easier to turn from idea into execution. If you have any questions or suggestions, feel free to reach out to us at 2211-289@tongji.edu.cn.